Okay, here's a challenging one because it brings vectors that we haven't used in a while back in. So go back to your day of the first day with projectiles, or maybe crossing the river and having to deal with two different directions at once. What we're going to do now is collisions where things move off at angles. I'm going to tell you right now, it's as simple as this. You simply have to conserve momentum in the x direction and in the y direction separately. So you're almost just making XY charts again. So if I take a look at this, where I had ball 1 moving towards ball 2, notice I don't have them along the same center line, so 2's going to, they're going to go off at angles. What I see here is simply I have 1 having initial momentum all in the x. But after the and 2 doesn't have any initial momentum, x or y. But after the collision, you can see that 2 moves off in the x. So I'm going to call that I guess I'll start with a P. I'm going to call that P2. That's the final momentum of 2 in the x. And I'm sorry about that sloppiness. And then I have P1's final momentum in the x. These two, even though it doesn't look very good to scale, the momentum of 2 and 1. Don't think this for a second. Don't think that 1's momentum, initial momentum of the system, becomes 1's final plus 2's final. This is not true. It's not as simple as that. 1's momentum initially was all in the x. So 1's momentum, this momentum right here, after the collision, it's got to be conserved, but it's not conserved in the, let me draw red lines here. 2's final momentum's in that direction. 1's is in this direction. If you add those red lines together, vectorially, you will get P1 initial x, but algebraically you won't. Because what you have, if you do it vectorially, the y components of those two arrows will cancel out, and you'll get a resultant that's all in the x direction. It's easier algebraically to see this. These two green arrows, P2 final x and P1 final x, they add up to be P1 initial x. So the x component of 1 and 2 after the collision adds up to the x component of 1, which happens to be the initial momentum of the system, after and before the collision. And that's all set here with m's and v's for you in a nice little equation that says P initial x equals P final x. This doesn't say that. This just tries to say that momentum's conserved. Well, it is vectorially, but not algebraically the way you try to do it. So you might see this written on the board in some college classroom, but really this is a better way for you to think about it. The initial momentum in the x equals the final momentum in the x. The red arrows are not in the x or y, so don't use those. The blue arrows are in the y. Notice that they're in opposite directions. Not only are they in opposite directions, I know that those two blue arrows, which I'd probably call P2 final y and P1 final y, they have to be equal and opposite. Why? Look down here. The initial momentum in the y has to be conserved, but both of these terms are 0. There is no initial momentum in the y direction. What that tells me is that these two vectors have to be equal and opposite so that they also add up to be 0, because the initial y momentum is 0, so the final y momentum is 0. What I'm saying to you here is 1 was initially moving all in the x direction. There was no momentum in the y direction before the collision. So even though you see two balls moving off in the y direction after the collision, their y momenta have to cancel. So if I were to boil this down into one thing quickly, it would simply be this. When you have objects go off at angles in a collision, simply conserve the x and y momenta separately. And again, these equations are doing it with m's and v's, and then the v1x, I actually break it down into a cosine theta. You can take a look at that on your own. You've done that a lot of times since the days of projectiles. Okay, the old T-bone collision. This is an interesting one. The initial momentum of 1 is all in the x. The initial momentum of 2 is all in the y. The green arrow cannot cancel the blue arrow because the x and y vectors are independent of one another. However, if you add them together, you get this arrow. What is the red arrow? The red arrow is what I would call the initial momentum of the system. Now, I just said to you, break these things into x and y components. I wouldn't necessarily suggest to you to Pythagorate the green arrow and the blue arrow. What is the green arrow? The green arrow is the initial momentum of 1. Initial. And what is and it happens to all be in the x. What is the blue arrow? The blue arrow is the initial momentum of 2, which happens, I wrote V1 initial, that should be a V2 initial. That happens to be M2 V2 initial, which happens to all be in the y. You can Pythagorate those two terms, and you'll come up with the red arrow, which is the initial momentum of the system. What good does that tell me? Momentum is conserved. That tells me that when these two guys collide, the final momentum of the system has to be this same arrow. So think about it up here as the Pythagorean of the green and the blue, and it's the initial momentum of the system. Down here, think about it as the final momentum of the system, because momentum has to be conserved. So now I have the final momentum of the system. Now the two objects don't have to stick together, but nicely if they do, this red arrow is the direction that they will move off in, because the momentum of the system has to be conserved. A cop can easily measure stuff like this at an intersection where an accident occurred to figure out how fast the vehicles were moving. So the initial momentum in the x is this green. It's this. The initial momentum in the y, all of this. Come on guys, come together. Okay, the initial momentum of the system is what you would get if you Pythagorate them, which I will do for you because it'll take me a second. And come on, well, the markers don't want it to be a second. So that plus, I'll keep my color coding together, and a squared plus b squared equals c squared. If I just want c, I got to Pythagorate like that. What is the direction of the initial momentum of the system? Well, I'm not doing it for you, but look. Put the arrows together and come up with that angle. You can do an inverse sine, cosine, or tangent, whichever depending on the sides you want to use. I'd prefer to go with tan because the green and this is how I'm literally going to do it. Tan is opposite over adjacent. So divide the green arrow by the blue arrow, or the magnitudes over here thereof, and you can come up with what the angle of the system was. What good does all of that do me? Well, what it tells me is the final momentum of the system has to be conserved. So the final x momentum has to be equal to what the initial x momentum was, and I can write, let's assume they stick together and go off like this. I wish I kind of had that in my diagram. So the initial x momentum was m1 v1 initial, which was all in the x. If they combine together, after the collision, they're going to go off with a certain velocity, and that velocity is going to have an x component, which simply means if that green arrow is the final, I should do that in red, if the red arrow is the final velocity of the system, the green arrow now is this v final x. Or if you want to put an m in front of these two terms, we can make these things the momentum vectors instead of velocity vectors. Okay, and then the initial y momentum of the system, which was m2 v2 initial, turns into their combined y momenta, which looks like that. So these two ugly terms with m1 and m2 in it are simply these arrows, and they have to equal, from the previous slide, even though not drawn to scale, they have to equal those original momentum vectors that we had on the other side. So if the cars collide and stick, what is their final speed? What you can do to find the final speed is simply take v final x and v final y, Pythagorate them, stick them together, find the final speed, and that's how fast the two objects are going. And I'm sorry I lost my color coding here. That should have been the blue. This should all be in blue. I'm sorry about that. And you can find the final speed. What you can also do is come back here, and when you Pythagorate these two momenta, that is in the direction of that red arrow. If you want to find the final momentum of the system, that happens to be equal to this. Now, this is in the direction of the red arrow. That's just V final. That's not a X or a Y. Notice that when I Pythagorated the initial momentum of the two cars, that was the initial momentum of the system. If I divide that by the combined mass, that V final here is this. I'll be specific here. That V that I'm getting after I Pythagorate the X and the Y. There's some pretty heavy vector component stuff going on there. Okay, I just kind of threw this in here. You can see an X and a Y direction going on, but there is also a case where momentum may not be conserved because the system's not isolated. So if you look at this question right here, I have a truck of mass M moving at speed V. The apple's going to come down and hit the truck. When the apple does that, it causes the ground to exert an larger upward normal force on the tires of the truck. To basically, the ground is going to exert an impulse that takes away the apple's momentum. That doesn't take away the truck's momentum, however, because this is in the Y direction. So when I see this picture, you want to think conservation of momentum like all of the other problems this chapter, but the apple's momentum is not conserved because the ground exerts an impulse to take it away. The X momentum, however, there's no outside force, just the truck and the apple. There's no outside force to take away or change the X momentum of the system. So the truck's initial momentum will become the truck plus apple's final X momentum. So momentum in this case is conserved in the X, but not in the Y. That's kind of interesting. So most all problems we do are isolated systems where momentum is conserved. But I'm just showing you here, there are situations out there where momentum may not be conserved in a certain direction because of some outside force exerting an impulse. Problem 23 of your textbook has this plate, the ground's attached to it. A plate falls, 23 is attached to it. The plate falls and hits the ground. Now, the first thing you might be thinking is, oh, okay, I've got an mgh of the plate becoming 1/2 mv squared of the plate. Okay, great. Well, what happens when the plate hits the ground? Well, problem 23 says it breaks into 3 pieces that go off in different directions. Here's the key, though. They go off in directions like this. I'm not doing a good job with my picture, but that's along the plane of the floor. What is this speed? In what direction is, when you set these two things equal, what would this speed be in? Well, it's going to be in the Y direction, if you will, or the downward direction here. Now, this is a 3-dimensional problem because once we get to the floor is a plane with its own, I guess I hate to get in the difference when the way the book did it, because the book may have called the floor the Z direction, so I'm sorry if it did. Okay, I'm going to change it right now. So the floor calls the height the Z direction, and it calls the width and whatever, the dimensions of your floor, the X and the Y. So even though you might look at this and think, hey, I'm going to figure out how much energy was conserved of the plate as it fell, that speed's not doing it any good because it's gone. That velocity is taken away by the impulse exerted by the floor. Instead, when I look at this, I would see a plate fracturing into 3 pieces. And what I would say is, in terms of the floor, the XY of the floor, there is no momentum in the X or the Y before the plate breaks. So in terms of the mo and the X, I'd say we start with 0, and then let's number these pieces, 1, 2, and 3. And 1 moves off in the X direction, 2 and 3 move off in the X direction. I got 3 pieces here. All the other problems you've seen have had 2. So I would write something like this. M1V1, this is after it hits the floor, moves off to the left, so I made that negative. And then for 2, I don't write M2V2, I write M2V2's X component, and then M3V3's X component. That is how I'd write an equation in the X along the surface of the floor for the 3 pieces. And in terms of the Y, that's a little bit easier because piece 1 doesn't move in the Y. So pieces 2 and 3, initially the plate was not moving along the plane of the floor, so there's no momentum there. 1 doesn't have any momentum. And then with these two, m2v2 sine theta and m3v3 sine theta, I got to make one of them negative because they're moving off in opposite directions. So I got 0 equals 0 plus, and you'll see these two terms do indeed add up to be 0. Those two terms in green would be something like these two arrows, the y components of 2 and 3, they got to be equal and opposite. The x components of 2 must add up to be the momentum of 1 in the x direction, in the negative x direction, if you will. So that would be a seriously complicated problem. But doable. Thank you.